Okay, now let's find the Taylor series of a function. Let's find the Taylor series of some function, let's say e to the 7x at x equals 2. And so what I want to do is I want to come up with a formula for the nth derivative of f at 2. So let's see if we can come up with a formula. So the original function, the zeroth derivative, is e to the 7x. First derivative is 7 to the first, e to the 7x. The second derivative is 7 squared, e to the 7x. And it looks like the nth derivative is 7 to the n, e to the 7x. And therefore, the nth derivative of f at 2, which is what we're after, is going to be 7 to the n times e to the 7 times 2, e to the 14. So e to the 14 is going to be some number, and then times 7 to the n. That'll be our nth derivative of f at 2. And then that's actually the hard work, because our function f is going to be the sum from 0 to infinity of the nth derivative of f at 2 divided by n factorial times x minus 2 to the n. So that's going to be the sum as n goes from 0 to infinity of, let's see, the nth derivative we said was 7 to the n times e to the 14 over n factorial times x minus 2 to the n. Okay, so that's how that works. That's how we would find the Taylor series of that function at the value of 2. Really, it's not any more work. Well, it's not much more work than doing what we did the first time for the Taylor series for e to the x. One other special case that comes up that I think is worth mentioning is what's called Newton's binomial theorem. So there's a binomial theorem which basically says, so the binomial theorem basically says, how do you take something like 1 plus x to the n, I'm just going to say n is 4, how do you expand that? And it turns out what you do is you write down, you have two terms. You have a 1 and an x. Let me actually write it like this so it's a little easier to follow. Let's make this x plus y. And so what you do is you write down, you have x to the 4th, y to the 0. You have x cubed, y to the 1st. You have x squared, y squared. You have, let me delete a little space here. You have x, y cubed, and then x to the 0, y to the 4th. And the binomial theorem tells you what are the constants that you put in front. You can get the constants from, what's that called, Pascal's triangle, or the binomial theorem. The binomial theorem is basically Pascal's triangle. And it turns out what these numbers are is, here you have 1, here you have 4. Okay, so that's 4 over 1. Next you'd have 6, 4, and 1. Okay, so I think the best way to think about those numbers is that these numbers are 4 factorial over 4 factorial, 4 factorial over 1 factorial times 3 factorial, so that's a 4, 4 factorial over 2 factorial times 2 factorial, 4 factorial over 3 factorial times 1 factorial, and then finally the last one is 4 factorial over 0 factorial times 4 factorial. And so you get this nice symmetry, okay, which is why you have a symmetry here. And these are what are called binomial coefficients. Sometimes these are written as 4 choose k. Okay, so that's 4 choose k. Okay, so those are binomial coefficients. If you've taken a course in statistics or probability, you've seen these before. They come up all over the place. And that's the binomial theorem. It just tells you how to find that. Newton, the super smart guy that he was, figured out that actually this pattern works even if you don't have an integer. So he showed actually that if you talk about, let's say you have 1 plus x to the alpha, what you can do is you can find the Taylor series at 0, so I guess it's a Maclaurin series, and you can write out what you're going to get. And it turns out what you get, at least for the x values between -1 and 1, is you get 1 you get x to the 0 times 1 plus alpha x plus alpha times alpha minus 1 over 2, which is basically what we got here. If you think about this term, this is 4 times 3 over 2, and 4 times 3 times 2 over 3 factorial. Okay, so you get alpha minus 1, alpha minus 2 over 6. And I forgot our powers here, so that's x cubed, and so on. Okay, and so here the point is that if this is our function f, the nth derivative of f at 0 is going to turn out to alpha times alpha minus 1, and you're going to have n terms here, and then you're going to be dividing by n factorial. Okay, so that's going to be what you get for the nth derivative of f at 0. Okay, and I'm sorry, I just said something incorrect. The n factorial comes later when you look at Taylor series. So the formula that you get is just alpha times alpha minus 1 times alpha minus 2, and so on. So let's look at an example here of this in practice. And what I'm tempted to do is to do this. Look at f of x as just the square root of 1 plus x, and let's find the power series. We know what we're looking for is f of 0, f prime of 0, f double prime of 0, and so on. And then we can plug all those into Taylor's formula or Taylor series and get our Taylor series representation for the function. So f of 0 is, of course, 1. F prime of 1, so this is going to be 1/2 times 1 plus x to the negative 1/2. So here, 1 plus x is going to be 1, so to whatever power is 1, so that's 1/2. The second derivative is going to be 1/2 times negative 1/2 times 1 plus x to the negative 3/2, so that's negative 1/4. And the third derivative is going to be 1/2 times negative 1/2 times negative 3/2, 1 plus x to whatever power. So the third derivative is going to end up being 3/8. Okay, and so then the fourth derivative would be 1/2 times negative 1/2 times negative 3/2 times negative 5/2. And you keep going. And every time you take a derivative, you keep multiplying by another term where you subtract 1. So what I mean by that is you have 1/2 minus 1 is negative 1/2 minus another 1 is negative 3/2 minus another 1 is negative 5/2. And so you keep multiplying by these terms where you're subtracting by 1. Let me add in the next term just to make the pattern a little bit more obvious. You got alpha times alpha minus 1 times alpha minus 2 all the way down to alpha minus n plus 1. Okay, and so this tells us that the square root of 1 plus x is going to end up being f of 0 plus f prime of 0 times x plus the second derivative of f at 0 over 2 factorial x squared, the third derivative at 0 over 3 factorial x cubed, and so on. And so that turns out to be, 1 plus 1/2 x plus the second derivative at 0 is negative 1/4. If we divide that by 2, we get negative 1/8. So negative 1/8 x squared. And next, the third derivative is 3/8. If we divide that by 6, we end up with 3/8 divided by 6, so that's 1 over 8 times 2, because the 3's cancel. 3 over 6 is 1/2. In other words, 1/2 times 1/8 is 1/16. We got 1/16 x cubed. Okay, and then you could figure out all the rest of the terms, the next terms. Okay, the numbers start to get a little bit unwieldy, but this is the Taylor series for square root of 1 plus x. Okay, so that turns out to also be very useful. It turns out that this is only going to work when x is between negative 1 and 1. The problem is a slightly different problem than what happened before. So the problem here is that when you take the derivative, this is undefined at negative 1, and therefore since it's centered at 0, and we have to stop at -1, then we also have to stop at 1, because we have it. Let me draw this. I think it's a little easier just to see. If you have a power series, here it's centered at 0, you know there's a problem at 1, but you can go all the way down to 1. That means that the radius of convergence is going to be at most 1, and therefore you can move 1 in the other direction. Because remember that we're always talking about an interval of some length centered at 0. So here our interval has to stop at -1, and therefore also it has to stop at 1. Okay, so I'm failing to recall exactly how this works, but my guess would be that -1 is not included, but 1 is. It might be that both of them are excluded, but we could look at that. All right, so that is some examples of actually finding Taylor series by hand.